Welcome back. In the previous video, we refactored our weapon trace code to get the beam end location. Now we're ready to start implementing strafing. And if you want to strafe, you need to know the offset between the direction you're looking and the direction that the character is moving. This is like a movement offset, and it's a yaw offset. Let's go ahead and take a look at what I mean. Now let's say I'm facing forward and I'm moving forward. So there's really no offset between the direction I'm looking and the direction the character is moving. But let's say I start moving to the right. Now there's a rotational offset between the direction that the character is moving and the direction that I'm looking. Let's illustrate what we mean. Now here we have a diagram representing our character in the world, and I have the red x-axis representing the x direction for the world, and the green y-axis representing the y direction for the world. So these are global coordinates. Now the character will be aiming in any particular direction at any time. We're going to be moving our mouse around, causing the camera to rotate around the character, and this is our control rotation, or the rotation of the controller, that's changing. And at any given point in time, the controller is aiming in a particular direction. Now if we rotate our aim a little bit so that we're aiming slightly off to the right, maybe 45 degrees away from the X direction, then this is what our base aim rotation looks like. Now our base aim rotation has a value depending on where we're aiming relative to the world axis. For example, if we're aiming in the direction indicated on this diagram, which is approximately 45 degrees away from the world x-axis, then our base aim rotation would be 45. Base aim rotation increases as we rotate clockwise away from the x-axis of the world. But if we're rotating counterclockwise, then we'll have a negative base aim rotation all the way to where we're facing the opposite way from the x direction, in which case we'll go all the way up to just before we reach negative 180. So base aim rotation is some value between negative 180 and positive 180. Now, at any given point in time, our character might be moving in any particular direction, and that direction is not necessarily the same direction as our base aim rotation. For example, consider this diagram. Let's say our base aim rotation is 45. We're looking in this direction, and we're moving in this direction, which is approximately negative 45 degrees away from the world x-axis direction. Now, when strafing, we need to know the difference between these two vectors, our base aim rotation and our velocity direction. Now, we can get the difference between these two rotations by subtracting them. If we subtract base aim rotation from the world rotation corresponding to our velocity direction, would be negative 45 minus 45, or negative 90 degrees. In other words, if we're looking in this direction and moving in this direction, our movement is about 90 degrees off from where we're aiming. And that tells us exactly how we need to strafe. We need to play a left strafing animation. So the key to knowing which strafing animation to play lies in the difference between our base aim rotation and the rotation corresponding to our character's velocity. Once we can get that offset, then we can use that value when determining which strafing animations to play and blend in between. So at any given point in time, while I'm moving, there's always some sort of offset between the direction I'm looking and the direction I'm moving. That offset is crucial to when we want to strafe, because that offset will tell us which sort of strafing animation we should play. Should we be strafing to the right, strafing to the left, or blending between any combination of them? So the first step to strafing is to get this movement offset yaw rotation value. Let's get started. We're back in Visual Studio, and I'm going to open up our anim instance class. This is where we're going to get and store that movement offset yaw that we were just talking about, because the anim instance can have the variable and we can expose it to blueprints so the animation blueprint can access that. And the animation blueprint is what needs that variable to determine which strafing animations to play and blend between. So let's go to shooter animinstance.h. And we're going to add a variable here in the private section. Let's call this movement offset and make it a float variable. Float movement offset. Now we're going to expose this to blueprints. So we're going to give it a U property, and we'll make this edit anywhere. Blueprint read write, category movement, and we'll use meta allow private access equals true since this is a private variable. We'll go ahead and give this a comment. And for the comment, we'll say offset yaw used for strafing. Now we need to compute this value every frame. So we're going to head over to the .cpp for shooter anim instance. If I'm in the .h and I want to move quickly to the CPP file, I can do Control-K-O and it'll move me over there. Okay, I'm here in Update Animation Properties. I'm going to scroll down. Now just under where we're checking to see if we're accelerating, we're still inside the check if shooter character. By the way, these dotted lines here allow you to know which block you're in if you hover over them. So we want to know our base aim rotation. What is the rotation corresponding to the direction we're aiming in? So let's make an F rotator and call this aim rotation. And we'll set this equal to shooter character, and we're going to call a function called getBaseAimRotation. This returns the rotator corresponding to the direction we're aiming in. Now we can print this to the screen by using a function on the G engine called add-on-screen-debug-message. To do that, we'll say if G engine and then call G engine add-on-screen-debug-message. Now there are some parameters here for add-on-screen-debug-message, and I go into detail about this in my book, Unreal Engine C++, The Ultimate Developer course. But for now, we just want to quickly print some text to the screen in the viewport. And so we're going to use a value of 1 for the key. Don't worry about what that means for now. 0 for the time to display, since we're printing this to the screen every frame. White for the F color. And we also need an F string for our message. So let's make an F string for the message to print to the screen. Right here, I'm going to create a local variable of type F string called rotation message. And I'll initialize it using the F string printf static function. Now this function allows us to create a formatted string and store it in an F string, just like we used formatted strings when learning how to use uelog. What we do is in printf, we give it a text string, so we'll use the text macro, and we'll say base aim rotation, and we can use format specifiers, such as a float specifier, so %f for float. And just like formatting a string in uelog, we have to provide the value for the format specifier, and it has to be a float. We're going to use the yaw from our aim rotation, so aim rotation.yaw. So we have an F string called rotation message, and we can pass that in to add on-screen debug message. Rotation message. This will print an on-screen debug message each frame in the viewport. Let's compile this. Now back in the editor, we're going to hit play, and you'll see that we're printing base aim rotation 0 to the screen. Now if I click in the viewport and I rotate, you'll see that it's increasing as I rotate clockwise. If I rotate about 90 degrees clockwise, then our base aim rotation is at 90. And we'll keep going all the way up to about 180, and if I pass 180, then it becomes negative. And now we're moving from negative 180 in the positive direction as I keep moving clockwise. And if I face the world X direction, then I'm back to 0 again. So that's how base aim rotation works. We also want the rotation corresponding to our velocity. So on the next line after our rotation message, I'm going to create a local F rotator called movement rotation. Now we want the rotation corresponding to our velocity. And there's a static library in Unreal Engine called Kismet Math Library that has a function that allows us to make a rotator from a direction vector. Now to use Kismet Math Library, we need to include the header file. So let's pull up the Unreal Engine documentation. And here we have U Kismet Math Library, and the include is kismet/kismetmathlibrary.h. Let's copy that, and we'll include this at the top here in Shooter Anim instance. Now we can use Kismet Math Library. So U Kismet Math Library, and the function we want to use is make rot from x. We want a rotator from the world x direction based on some direction vector. And because we're in Shooter Anim instance, we have access to the character. We can get the character's velocity like we did up here with Shooter character get velocity. So let's use that in make rot from x. We'll pass that in. Now these are getting unwieldy with our big font. So I'm going to use multiple lines for these, like so. And same for this one. I'm going to use multiple lines. Okay, so we have our movement rotation. Now why don't we go ahead and print a message to the screen showing our movement rotation, kind of like what we did with our aim rotation. So we'll make an F string using printf like we did with rotation message. So copy rotation message, and we'll call this movement rotation message. And for the text, we'll say movement rotation. And for the float value, we're going to use movement rotation.yaw. Now in our call to add on-screen debug message, instead of rotation message, let's print movement rotation message. I'll go ahead and compile this. And in the editor, I'll press play and I'll move. Now notice, if I'm moving forward in the positive x direction, movement rotation is close to 0. If I'm moving to the right, it's close to 90. If I'm moving backward, it's close to negative 180 or positive 180. And if I'm moving left, it's close to negative 90. Okay, so we have our aim rotation and we have our movement rotation, and we want the difference between these two. Luckily, Kismet Math Library also has a function that can take the difference between two rotators. Now we really don't need to use our rotation message anymore, so I'm going to use a multi-line comment to comment that out. I don't really need our movement rotation message either, so I'm going to use a multi-line comment to comment that out as well. Now I'm going to take our movement rotation and move this just under aim rotation. Now remember, we created movement offset. It's a float here in Shooter Anim instance exposed to blueprints. So we're going to use that variable to get the difference between these two rotators. So let's say movement offset equals U Kismet Math Library, and the function we're going to use is normalized delta rotator. And we want the difference between movement rotation and aim rotation. Now this function returns an F rotator, and movement offset is a float. We only want the yaw, so we're going to get the result from this function, which is an F rotator, and get the yaw from that, so dot yaw. Now since movement offset is a yaw, why don't we change its name to movement offset yaw instead of just movement offset, and that'll be a lot more descriptive. So this gives us our movement offset yaw. Now finally, we can make a string message to print to the screen so we can see the value of movement offset yaw. Why don't we go ahead and do that? So just below our commented out strings, I'm going to paste the rotation message I just copied here, and I'm going to call this offset message. And for the text, I'm going to say movement offset yaw, and I'm going to use the value movement offset yaw in the formatted string. And finally, in add-on screen debug message, we're going to print offset message. Let's compile this. Now in the editor, I'll hit play, and we have our movement offset yaw, and it's 0, and that's because our velocity is 0, and we're facing the positive x direction. I'm going to click in the viewport, and I'm going to move around, and as I move to the right, I'm looking forward and moving to the right, which means our movement offset yaw is 90. Now if I move to the left, it's negative 90. And if I change my aim direction and I keep moving to the left, we're about negative 90 degrees. So that should tell us a value for our offset yaw of -90 means we should just play our left strafing animation. Now if I use the A and W keys together, I'm moving in about -45. And as I move my aim direction, we're staying roughly close to -45. So as you can see, no matter which way we're aiming in the world, our movement offset yaw is always going to reflect the difference between our velocity we're moving in and our aiming direction. So this gives us a value from -180 to +180 that we can use to map to certain strafing animations that we can blend together. So this value is what we're going to use while strafing. Okay, so back in the anim instance, I'm going to go ahead and comment out this last string that we printed, and I'll go ahead and comment out this call to add on-screen debug message, since we don't really need these anymore. So the takeaway is we now have this movement offset yaw, which we've exposed to blueprints, and we'll be able to access this in the animation blueprint. In the next video, we're going to look at making a blend space and making use of movement offset yaw so that we can blend between strafing animations. See you in the next video.